Here we go.
So here's the section 3.1 pre-calculus instructional YouTube video. So we're just going to be doing a couple problems, talking about sketching graphs of exponentials and transformations of exponentials. So like we look at something like f of x equals b to the x. So if we have like this, where b is some number that's greater than 0. If b is greater than 1, then we have exponential growth. If b is between 0 and 1, then it's exponential decay. All right, this should be reviewed, but just going over a little bit. So now, f of x equals b to the x is always going to have some similar properties, well, the same properties. So it's always going to have a y-intercept at 0, 1. If I replace x with 0, something non-zero to the 0 is just 1, so we get 0, 1. We are going to have a horizontal asymptote at y equals 0. That function will have a horizontal asymptote at y equals 0. The domain is going to be negative infinity to infinity. The range is going to be 0 to infinity. All parentheses there. And let's talk a little bit about the difference between growth or decay. So if I have b is greater than 1, what's going to happen is I'm going to have a point right here at 0, 1. And if b is bigger than 1, so if I make this x equals 1 instead of x equals 0, what's going to happen is I'm going to multiply this value by b. And then if I get x equals 2, I'd get b squared, so I'd multiply the y value by b again. And if b is a number bigger than 1, that means these are going to get bigger and bigger. We're going to get that exponential growth. And then as I go negative, I'm going to be dividing by b over and over and over again, and that's going to give me smaller and smaller numbers. It's still going to be a positive value, hence the greater than 0 for the range, and having that asymptote at y equals 0. So this is when b is greater than 1. If we have 0 is less than b is less than 1, we're going to get it looking the other way. We're still going to go through here at 1 or at 0, 1. But because this is a small number, like a half or a third or 0.9, when I multiply by it, in other words, when x is 1 or 2 and I'm multiplying by that b value, my numbers are going to get smaller and smaller to the right. And if I divide by a small number, like divide by a half or divide by 0.1, dividing by a half is multiplying by 2. Dividing by 0.1 is multiplying by 10. So what happens is we get this on the other side. So that's why this is exponential decay when b is less than 1, still greater than 0. Exponential growth when b is greater than 1, because as x increases, so like x goes from like, let's say 3 to 4, your y value gets multiplied by your base, your b number. If your b number is a big number, multiplying by a big number is going to make it bigger. If your b number is a small number between 0 and 1, multiplying by a small number will make it smaller. So that is that. Let's talk about just graphing f of x equals 10 to the x, just real quick. Right? No transformations, just 10 to the x, so we've got the point 0, 1 here. If I go over to 1, then I gotta go, well, 10 over 1 is 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I go over to 2, the next point would be 2, 100, because I'd multiply this by 10, where 10 squared is 100. So here I'm just going to go, woohoo! Like super high up there, because 100 would be way up there, through my ceiling probably. And then as I go negative, I'm going to get this point right here, which is negative 1, 0.1. Because 10 to the negative 1 is 1 over 10, right? It's a reciprocal. So I get just this really steep on one side and really close to this asymptote as I go to the left, but it's never actually going to cross over or touch 0. It's just going to keep going like 0.1, 0.01, 0.001, 0.00001, and on and on and on. Okay, so that's f of x equals 10 to the x. If I have f of x equals 1/10 to the x, actually I'm going to do that over here. F of x equals 1/10 to the x. I'm still going to have the same y-intercept, still going to have the same asymptote, but it's going to be on the other side. This 1/10 is less than 1. So if I go x is 1, and I multiply by 1/10, I'm going to get 1/10, and then I'll get 1/100. So on the right, my graph is going to decay to the right. If I go to the left, if I divide by 1/10, that's the same as multiplying by 10. So I get a graph that looks like this. Basically, these are reflections of each other because 10 to the negative x is the same as 1/10 to the x, right? Because this is 10 to the negative 1 to the x. So purple is 10 to the x. The graph in black here is 1/10 to the x, which is the same as 10 to the negative x, the reflection in the y-axis. Now, if we look at e to the x, f of x equals e to the x, right? We get 0, 1 still. And then the number e is about 2.718. It continues on. So 1 times e is e. And then e squared is about like 7.4. 1, 2, 3, 4, 5, 6, 7. So 7.4. So the graph looks like this. And then as I go to the left, it decays. So this is y equals e to the x, approximately. So now, e is just a special number. It's this wonderful number, actually, where if I pick any point here, let's say I pick this point right here, where the y value equals 1, 2, 3, 4, 5, 6. If the y value equals 6 here, the area under the curve, all of this, if I add all that up, that area is going to equal 6 units, 6 square units. And the slope of the line, the slope of the tangent line to this curve right here, is 6. It's a really, really cool function where every y value represents the slope of the curve at that point and the area under the curve to the left of that point. So it's really cool. And it's really helpful in calculus. It's really nice in calculus. All right, we're just going to, so those are some basic functions. We're going to talk about making a couple of transformation graphs. All right, let's say we have f of x equals -3 times 2 to the x plus 1 plus 4. What are our transformations? And then sketch the graph. So I'll let you go ahead and state your transformations while I erase over here. And what's the parent function? I should ask that too. So here, the parent function is g of x equals 2 to the x, right? The base is what tells us what our parent function is. All right, so transformations. Well, we've got a negative on the outside. We're multiplying by -3, so it's going to be a vertical stretch by 3 and a reflection in the x-axis. So those are both acting vertically. So here we have reflection in the x-axis. We have a vertical stretch by a factor of 3. We have this plus 4, which is a shift or a translation up 4. And then we've got this x plus 1. Remember, with the x plus 1, to see what that does, we can just take whatever it is, set it equal to 0, and find our new starting point. So we go like -1, x equals -1, which means we shift left 1. So we shift up 4, left 1. So now we're going to graph it, and there's a couple ways that we could graph it. We could think about y equals -3 times 2 to the x, which would look like this. It'd be like 2 to the x looks like this. Right, if I reflect it and put that -3 in front of it, right, instead of being 1 away from the asymptote, it'll be 1, 2, 3 away. And it's basically going to look something like that. So I've got this -3 times 2 to the x here, and then I can just shift it up 4. 1, 2, 1, 2, 3, 1, 2, 3, 4. Right? 1, 2, 3, 4. So really it should look like that. Just shift it up 4 and then left 1. That is not my personal favorite way to do it. You could do it that way, but what I like to do, is I like to say, well, we got to shift up 4 and left 1. So the up 4 tells us that we are going to have a horizontal asymptote at y equals 4. The left 1 tells us instead of starting on our y-axis, we're going to start at y equals 1. So now what we're going to do is we are going to pretend that this is our y-axis and this is our x-axis. So we're pretending that the orange is our x-axis and the green is our y-axis. And we're going to try to graph this -3 times 2 to the x on this new set of axes. So starting here, this is like our new origin, 0, 0. It's not actually the point on the graph. I shouldn't have put something there. But what we're going to do is we're going to say, well, it's -3 times 2 to the x. Normally, 2 to the x has a y-intercept at 0, 1. But it's being multiplied by -3. It's that reflection and a stretch. So instead of being 1 away from the asymptote for our y-intercept, we are 3 away. Now, if I go 1 more to the right, 1, 2, 3, 1 more to the right, I'm going to double this distance from the asymptote. So instead of being 3 away, I'm going to be 6 away. 1, 2, 3, 4, 5, 6 away. And then I would do that again. I would be 12 away for my next step. So this distance here would be 12. So this would put me down here at -8. Because 4 and 8 make 12. Now as I go this direction, I'm going to divide the distance from the asymptote to the point by 2. So I divide by 2, I'm 1.5 away, then I'm 0.75 away, and so on. And we get our graph looking like this. Okay. So what I did here is I said it shifted up 4, that's my new horizontal asymptote. It shifted left 1, so I just think of x equals -1 as my y-axis. And then I use what I know about the graph of just -3 times 2 to the x, or just 2 to the x reflected and stretched. But I do everything from the new horizontal asymptote, which is like my x-axis, and my new y-axis. That's kind of a different way of thinking about it. All right, we're going to do another example, and then that'll be it. All right, let's say we have f of x equals, let me erase this first. F of x equals 3 to the -x plus 2. So I want you to sketch the graph of that. state the transformations first and then sketch the graph. Okay. So, who's this color? This one. This negative is going to be a reflection in the y-axis. It's acting on the x, so it goes in a horizontal direction, which is over that y-axis or in that y-axis. So for transformations, we have a reflection in the y-axis, and we have a shift not blank, we know it's 2 units, right? 2 units to the blank. And we're going to say, is it right or left? And remember, the way to figure this out is to take the argument of the function, which is negative x plus 2, make it equal to 0, and solve for what x is your starting value x. In other words, what number do you have to put in for x to make it equal 0? So here to solve this, to easily solve it, I can just add x to both sides and get x equals 2, which means it has shifted 2 to the right. Right? Even though it's a plus 2 here, the negative on the x, that reflection, goofs it up. So here it's 2 to the right and a reflection on the y-axis. So one thing we could do to graph this, we could say, well, 3 to the x looks like this. Right, where it's like 1, 3, 9 for our y numbers. And then 3 to the negative x is just going to be the reflection of that. So over here we have 1, 3, 9. And then I could just take this and move all the x's plus 2 over. So 3 to the negative x plus 2. So this 1 is going to be over 2, this 3 is going to be here, this 9 is going to be there, so it'll look like that. Okay, or, that's one way to graph it. The other thing you can do is say, hey, we shifted it right too, so let's just pretend this is our new y-axis. Let's just pretend. Well, let's graph 3 to the negative x here. Well, 3 to the negative x is going to have a y-intercept at 0, 1. The y value is going to be 1 away from our asymptote. Now, if I go to the right with a negative x, it's going to get smaller. So it's going to go to like 1/3 and smaller, right? Asymptote. If I go to the left, it's going to multiply by 3. So 1, 2, 3. If I go 1, 2, if I go 1 to the left, it goes up to 3. 1 more, multiply that by 3 again. I get up to 9, and there's my graph. All right, I don't know how helpful this video was. Hopefully it was somewhat helpful. If not, find me in office hours, and thanks for watching.